And go ahead. Yeah, I'll give you 5 minutes and I'll give you 1 minute.
Okay, good morning, everybody. So it's another great workshop. What I'm going to show you today is it's a bit more unusual for what we do, and it's more technological, despite the fact that we're in a fundamental physics workshop. So I hope you'll like it. I come from the French Atomic Energy Authority, CEA, in Saclay, near Paris. And I'm going to talk to you about interface chemistry between an electrode and a technological layer of PZT. In past workshops, we've shown quite a lot of work using electron spectroscopy and combining it with spatial resolution to image electron emission from surfaces and to image, in particular, domain structures, domain walls in ferroelectrics, ferroelastics. Here, we sacrificed the spatial resolution, and instead, thanks to tuning the photon energy that we're going to be using to carrying out electron spectroscopy, we're obtaining depth resolution. And this allows us to look at surfaces, and it will allow us to look also at interfaces buried beneath several tens of nanometers beneath the surface. So the object, the material in question, is PZT. It's a morphotropic phase boundary. Why do we do this? It's so indicated, or it might be indicated if I could get it to work here. Surface-mounted devices take up a large area on PCBs. If you replace them with integrated passive devices, much smaller footprint, but to get the same performance, you need to increase, for example, the capacitance density. And the solution for doing this is twofold. On the one hand, you can change the materials, and that's what we do here. You can use a high dielectric material, such as PZT, and then there's an architecture-based solution, 3D multi-beam metal, insulator metal, which is indicated here. So we're combining the high dielectric constant expected from PZT with favorable architecture. Now, it's not that simple, obviously, and in particular, the role of the interface is very important. Are the electrodes that you use, do they provide sufficient screening to stabilize the ferroelectric state? Or is there a remnant internal field? If the electrodes are asymmetric, are the bands skewed, changing the band structure of the capacitor? Do electrons spill over from the electrode into the dielectric, basically meaning that you're metallizing a thin layer, or at least creating an altered thin layer? Is there a specific interface chemistry? And then other questions such as adhesion. Adhesion is illustrated here. A favorite electrode on CMOS-compatible capacitors could be platinum. But when you use platinum, in fact, that delaminates after a certain number of cycles. And so the solution is platinum with a thin ruthenium layer between the platinum and the PZT. And there's no delamination, and that's something we're working on quite recently. Another problem with PZT, of course, is that it's volatile. There's a whole lot of annealing steps to be taken during processing, and so you lose lead. To compensate, the solution is quite simple. You just increase the lead content in the precursors. Well, if you increase lead content in the precursors, then maybe you're changing the stoichiometry, and maybe you're changing the dielectric constant. So there's quite a lot of optimization to be done before you can use this material in realistic devices. So here are the samples. It's industry-ready processing, wet chemistry, sol gel. There are basically 4 layers. Each layer is about 50 nanometers thick. And these were made with varying lead precursor excess. In fact, this is what the sample looks like. It's a standard silicon wafer. It comes from ST Microelectronics. Adhesion layer, bottom electrode. And then we use different seed layers with different lead excesses, 10, 15, 20, 30%, and the last layer as well has the same lead excess. There's several annealing steps, drying, pyrolysis, and then rapid thermal annealing to show the crystallization and therefore the ferroelectric properties. Technique we're using, photoelectron spectroscopy, is photon in, electron out. This is what we want to know. The valence band, the core levels with the chemical signature, valence states, so on and so forth. This is what we measure. It's a spectrum which looks like this, or a spectrum which looks like this, and as a function of the kinetic energy with the core levels. And knowing the work function, knowing the incident photon energy, we hope to be able to deduce the initial states of the electronic structure and the valence structure. Very important is that this is essentially a surface-sensitive technique. Here is the energy, the kinetic energy of the photoelectrons, and this is the inelastic mean free path distance traveled before undergoing some kind of inelastic collision and therefore losing energy. And it's round about a nanometer for typical electron energies. So we're looking essentially most of the time at the surface of our samples. Some SEM characterization as a function of the lead content at low lead excess in the precursor. Lots of nanostructures. These are about 10 nanometers to 15 nanometers in diameter, average, quite dense, covering about a fifth of the surface. They get less dense here, they increase in size, they almost disappear when there's 20% in there, they completely disappear, and the grain size of the PZT is much, much bigger. So there is a clear effect of the lead precursor. You can see this in the XPS. The lead core levels don't change. That means that the lead chemical state and local environment is always the same, whatever the lead excess level we use. However, this is not the case for the zirconium. For the 10%, there are clearly two environments. One is that associated with PZT, and the other one is at higher energy. And as we're going to see, it's actually it is associated with these nanostructures, which are more like zirconium oxide. This second component decreases with increasing lead precursor excess, and effectively at 30%, there is no more nanostructures, and this second high binding energy component has disappeared. Looking in more detail at the 10% sample, this is done as a function of takeoff angle, so we actually go to more glancing emission here, and the second high energy component has increased, confirming in that it's surface nature, so it's correlated with these nanostructures. We've then spotted the surface, and this second component disappears. So once again, we've removed matter from the surface. This corresponds to those nanostructures. And finally, the oxygen 1s, when we go to more glancing emission, again, this second component, which is related to that surface phase, surface nanostructures, has increased in intensity. So we can do some quantitative analysis, and basically what we have is a discontinuous surface layer of 15 nanometer diameter ZrO 1.89 nanostructures, almost ZrO2. Final information on the film before putting down the electrodes. X-ray diffraction. In fact, the lead excess can also change the preferred orientation of the sol gel layers. That can be quite important for the absolute value of the polarization you obtain. And this is glancing angle X-ray diffraction. In other words, very sensitive to 30-40 angstroms, 3 or 4 nanometers on both the PZT-10, the PZT-30. PZT-30, nothing really to report. All the expected peaks are there. PZT-10, confirmation of the crystallographic structure of these that surface phase, the nanostructures. We have peaks corresponding to ZrO2. So we're pretty confident of the chemical nature of that layer. Now we grow the electrode, our ruthenium platinum electrode. Here we have cross-sectional TEM, and what we see is that these nanostructures have been preserved. There they are. So the electrode actually follows that topography. You look at some energy loss. It confirms the chemical nature of them, as observed in XPS. There's zirconium and oxygen. And what we also see in the electrode characterization is there's a strong offset, there's a strong imprint, there's an internal field there after deposition. Other electrical results on these capacitors now as a function of the lead excess. First of all, the capacitance density, the surface area, actually increases with increasing lead excess. So this is quite important. It's 10%. It's quite significant. The loss tangent decreases, which is good as well if you want some high-performance devices with lower power consumption. But unfortunately, there is the breakdown field actually decreases with increasing lead excess. And the decrease is quite important. It goes from 1.6 to 1.3. If we use a two-layer, simple two-layer, a very simple two-layer capacitor model, The only assumption here is the dielectric constant of these nanostructures of ZR02, so we assume 25. And what we would expect then is that the device made with PZT10 would be about 0.86, have a capacitance of 0.86 of the device made with PZT30, which essentially is what we see. So it's far better than an order of magnitude agreement. The decrease in the breakdown field, what we suggest, to be confirmed, but what we suggest is that it's due to the band gap of ZR02, which is about 5.8 eV. It's about almost twice that of PZT. And so this creates a barrier. This creates a more efficient barrier to breakdown and therefore improves the performance. So we can see that there are contradictory tendencies here as you increase the excess, and technologists, they have to choose where is the optimum value for the lead precursor. Now we want to look at the chemistry of this interface, and we do this with what's called HAXPES, which is hard X-ray photoelectron spectroscopy. Standard X-ray photoelectron spectroscopy, as I showed you on the surface, allows you to look at the first nanometer or so of the chemistry and the electronic structure. And this is because of the inelastic mean-free path. Now, if you do the same analysis on the same levels, but using much harder X-rays, for us, hard X-rays are several kilovolts, not the tens of kilovolts in the SRF or in argon, as the last speaker showed us, then what we get is this. The inelastic mean-free path goes up to about 10 nanometers, and basically that means you're getting information from the first 25, 30 nanometers. So you can see through a top electrode, a realistic top electrode, not some ultra-thin thing which is discontinuous and is probably not even a real metal, but something like 10 nanometers. It's reasonable, it's continuous, it's going to screen as a technological electrode would actually do, and you can look at this interface providing that there is a distinctive chemical signature coming from that interface. So that's what was done. The experiments were done at the Soleil Synchrotron Galaxy's beamline. This is do-it-yourself operando. Do-it-yourself because this is what the sample holder looked like. Okay, so there's bits of copper to ensure the two contacts is about the same size as a 10-cent piece. We've glued the thing onto some circuit board, but it worked. In our case, the bottom electrode is grounded, and we're biasing the top electrode. And this allows us not just to probe that buried interface, but also to get the response, the signature, chemical and electronic signature, under bias. In other words, under real operating conditions. So here's the first results. This is a reference spectrum without the top electrode. All the usual core level peaks are there. We put the top electrode down, and then effectively, on this scale anyway, we've almost completely attenuated the signal coming from the PZT. This is just to underline the need for probing down below that electrode and using hard X-rays. Here are the raw data. The two bias states we used were +3 and -7. That was because you remember the electrode characteristic, there was an offset. There was a 2-volt offset. So these values are actually symmetric around that measured butterfly loop. So the spectra are offset by 10 volts. If you correct for that, then of course the electrode core levels coincide. But you can see here there are residual differences in the emission coming from the PZT. And these residual differences are therefore due to the polarization state affecting the PZT near the interface. These are the results. This, again, is the reference without the electrode. That's why the statistics are much better. Here's a bit noisier. We can see three things. First of all, this is the component due to the zirconium. It includes both the nanostructures and the zirconium in the first layers of the PZT. And these are the components due to the lead. What we see is that as the bias changes, the whole spectrum is shifted. Remember, we've corrected for the applied bias. So this is polarization due to internal field in the PZT. Secondly, there is this additional peak. It's a singlet Therefore, it must be related to the zirconium 3S. It can't be related to the lead. And this exists also for all biases. So what we know is that these nanostructures are present at the interface, that as the bias changes, there is a polarization-induced shift in the electronic levels at the interface, and there is some specific interface chemistry. So I'll conclude there. Just to remind you, we looked at the sol-gel PZT layers. There is, depending on the lead excess, we have there can be a low dielectric layer based on zirconium oxide. This layer reduces the capacitance density and loss tangent, but it improves the loss tangent, but it reduces also the breakdown voltage. There's a specific interface chemistry. The screening, despite the solid electrode, is imperfect, and this gives rise to an internal field. There's one thing we haven't in these technological samples considered, is that the sol-gel is grown thick layer by thick layer, and we haven't considered what happens at the interface between these layers, which is probably an important point. So that's about it. These are the people who did the work. Ibrahim Aghe was the guy who did his thesis on this, and he's just graduated. And just to reassure you, or to reassure me maybe, I hope next time we'll be able to report some nice data on domain walls in a completely different systems, calcium titanate. Here we have the electron image, here we have the AFM. We can look at angles, and we can look at polarity in the walls. So we'll go back to that, I hope, next year. Thank you.
Questions? Microphone.
Thank you for the talk. Can you quantify the magnitude of the internal field as a function of the polarization?
Yes, I can't.
What does happen if you change the polarization, for instance?
Yeah, I mean, we can. It's quite simple to do. We just look at the offset. I can't give you the figure there. I can't remember the figure. But yes, we can. We can indeed. I'll show you that afterwards if you want.
Yeah, come on up.
I understood. Nice talk. Thank you for doing these measurements on those nanoparticles that the community has often thought it's pyrochlor.
Yeah.
One quick question. When you look at the orientation of the films, if I understood correctly, you seem to suggest that when you do not have enough excess lead, you do get a 1-0-0 orientation. This seems to be somewhat contrary to a lot of other literature reports in which when there is higher excess lead, you do get more oriented films because the lead oxide excess is a sheet layer and therefore allows a 0-0-1 orientation. Can you comment on that?
We've seen this it's reproducible first of all, so it's a real result. But it may be to do with the exact temperatures we've used for the crystallization. We do 2 rapid thermal annealings, one after the first layer, which is the seed layer of the PZT, and one that. And as you know, because of the crystallization temperatures, there's a strong gradient between the titanium and the zirconium in each layer. So what goes down first is titanium-rich. And it's titanium-rich, so you at the bottom of your layer, you will have PTO, or almost PTO. So in fact, what we're looking at is in that seed layer is the growth of PTO on platinum, rather than PZT. So this may have something to do with it.
Might want to talk later.
Yeah.
Thank you.
Yeah, come on up. And can we have the next speaker come up too, please?
Tell us a little bit about your sol-gel. Did you make that sol-gel? Can you tell us the basis of it? Or was it commercially acquired?
It's I did not make it. It was done in clean rooms in the CEA in Grenoble. The solutions, I think, were bought from Japan. They have a standard. I can give you a bit more detail in the papers.
All right, thanks.
Yeah.
Okay, with that, we'll thank the speaker again. Thanks.